Видна картинка, ну вот фотография с shared screen.
Меня слышно?
Да, слышно. Слышно. Я послал ссылку на доску. Но
Сейчас.
там еще имеется сейчас картинка от Саши Смаля, которая, как я понимаю, прям лично им сфотографирована в старом здании Техниона. Как то место физическое, где был разработан алгоритм Лемпеля-Зива. Так я думаю.
Да, но при этом и тем не менее, эту табличку повесил.
Ну да, нет. А что в этом такого странного?
Ну и
Не-
Е
не-
вроде бы в Америке, а не в Израиле.
Нет, но оно в Америке, но оно, так сказать, отмечает это самое памятные места везде,
Ну, понятно.
я думаю.
Наверное.
Так, а уже доска, значит, транслируется, да? То есть мне надо только за нее зайти.
Доска
Правильно?
транслируется. Это первая страница доски, да. Я могу переключить на вторую, и там даже написано Лемпель-Ziv.
Не, можно оставить пока.
Да,
Я просто...
да.
Так, значит... Все-таки мне, наверное, надо будет прийти на эту доску. А, не то. Еле успел. Фух,
Что, не действует доска? В будущем году,
действует.
кстати, Google отменит, к сожалению, этот самый Jamboard закроется, увы.
Невелика печаль, честно говоря. Он
А
всё
чем
равно
ты
с моим-
пользуешься?
Ну, я пользуюсь вообще-то просто, ну, это не коллективная моя личная доска, когда мне что-то надо писать, я пишу в своем Samsung Notes, там все очень хорошо пишется.
Нет, ну так-то можно писать и на бумажечке. Нет, а вот именно вопрос...
Нет, ну на
если-
Нет, ну я могу это транслировать
Ну
другим.
да. Нет, а какой-нибудь
Нельзя,
коллективной
чтобы ты
доски
приходил и переправлял все. Этого нельзя.
Нет, а как коллективной доски ты не видел хорошей?
Ну, есть этот ядро, но он мне не очень нравится. А с Гуглом у меня такая проблема, что на планшете там постоянно артефакты возникают, то есть когда начинаешь писать, он какие-то лишние линии проводит. Я подозреваю, что Samsung специально испортил работу с Jamboard, чтобы люди не пользовались. Ну, другого объяснения я не могу придумать. Почему в Samsung Notes никаких таких проблем нет, а в Jamboard есть. Ну, собственно, испорчено на самом деле все, что через веб-браузер делается. Может быть, нужно правильный браузер найти.
Ну, вообще в Jamboard есть этот самый... Ну, это сейчас все уже не актуально, но было приложение андроидное.
Ну, правильно, нет, оно... Нет, запускается, конечно, приложение. Ну да, запускается
В каком смысле
приложение,
через
поэтому
браузер
причем тут...
тогда, да.
Да, браузер это ядро как раз. У ядро, по-моему, нет приложения. Так что все равно я подозреваю Samsung в нехороших, нечестной конкуренции.
Just for
не знаю,
Thomas,
зачем
we are
нужно. У
just
них
whining
очень хороший
about
блокнот.
Jamboard, which will stop working next year, and asking for whether someone knows some good shared whiteboard, but yeah. And Vereshchagin disappeared, or no, he is not visible. Yeah.
Я здесь.
Yeah. So just if someone can just switch on the camera, it will be better for speaker to see this content immediately.
Will I see anybody, in fact? That's a question.
Sorry?
How can I see? So, I have to...
There are
The
participants.
problem is that if I'm not sharing, I cannot see the faces because...
Why? You just should put participants on, and then you will see.
No. I mean, you're sharing the Jamboard, right?
Yeah.
And then when I'm going to this Jamboard, I'm just closing my Zoom and I don't see any faces.
No, of course, if you
right?
close
So
your
then,
Zoom, you.
Well, how you know? Usually when you share, then you know. The
Okay,
Zoom
but
closes, it
just
has
start
faces,
sharing
so.
start sharing your. As I will stop sharing, and you will start.
Yeah.
It's obvious.
Yeah.
How do I stop it? Hello. Stop share. Yeah.
Well, I wouldn't say that it wasn't obvious. Yeah, but I just. Share. As my mom was telling me.
Yeah, so we see your board. The only disadvantage is that we see some also all other information which we should not see, but
We should not see. Well, I don't see anything compromising me, I think.
no, it's no, we did not check whether the sites could be compromising you.
Okay, so should I start?
I think the worst thing that we can see is the subject of one of your emails in Gmail. One of the tabs.
Yeah.
You may press F11, then we will just see the board. That's it.
What, F11?
Yes, F11 it should be.
I have no idea. I don't know how to make the full screen.
Okay, no, but it's not really. We
Okay,
just
whatever. So
there are no
I can
complicated
start.
formula. Yeah, so let's see who is there, and it seems that yeah, okay.
Well, Tomasz is here. He knows some
Yeah.
Russian, but I think not.
No,
not
no.
that.
I guess it's better if
We
No,
won't
if
touch.
you can,
English is better.
if you can speak Polish,
Yeah.
it would be an interesting experience.
Yeah.
no, but this is
No.
only for Sasha, not for Thomas.
It's the worst variant of all.
Yeah, okay.
Yeah, okay.
So you can show the
so-
first page. So Sasha
no,
Smile will
the
see
first
his
page.
nice picture, and everyone.
Thank you.
Yeah, but in fact there are specialists. So I will talk about some Lempel-Ziv algorithm,
Yeah,
and I'm not sure. So it has some papers, one from 77, one I probably, and I'm not sure that this one that I will be telling you. I mean, I should have looked to the papers before the talk, but I don't know.
yeah. But anyway, the entire thing is for a long time. I would like to know what is written in Lempel and Ziv papers, and it was always unreadable. And finally, Sasha explained me very simply what is claimed, and why it's true, and everything is clean. So I hope we will enjoy whatever is written.
Yeah, okay, so I want to start with some remark. So about prefix-free coding. So that we can use, so there is this, a standard observation that we can use prefix-free coding for compression of long strings. Let me just, so, okay, if I have, let's say some string of length n in some alphabet, sigma, what I can do is, I can just look for any letter of the sigma of the alphabet, how many times it appears in a string. I don't know, let's denote it by, I don't know, theta L. And then what we can do for compression,
We can provide for this distribution. We can provide a prefix-free code whose average length per symbol is close to the entropy of the random variable.
Yeah. So the idea is that then we could construct. So we will try to code. We want to consider some code for letters of sigma, prefix recoding, and we want to construct. Let's say then it makes sense to consider a code which has optimal average length with respect to the distribution which is produced by the numbers of occurrences of the letters in the word, right? So it will be something like, so we have to normalize these occurrences by the number of letters, right? So this will be, you know, this. I don't know, if I have k letters in the alphabet, this will be this distribution. And then I take, I don't know, let's say Huffman code for this distribution. And let's say its average length is L. So L is that's the average of this distribution over letters of sigma and times the length of the code of the letter sigma. Then we are just using, we are coding our word by every individual letter by its code in this code. And then we'll see that since it's prefix free, then we can decode the word back from its code, because we can go from left to right and see where the code of each next letter ends. And then the length of this code will be n times L, because just the letter L appears theta L times, and when we divide by n, we have this average length.
And so,
then there
are two different things. There is a Huffman algorithm to finding the optimal code, and also what is called the Shannon-Fano result, which says that this thing is between h of psi and h of psi plus 1.
Yeah, where by psi we mean the distribution over which we, with respect to which we're trying to minimize the average length of
just the frequencies, frequencies.
Yeah. And so what in the end we obtain is that we obtain that we can compress our string to something which is at most this thing, h of whatever it's called, I forgot, zeta or something.
No,
I have troubles.
What I tried to draw was psi, and
psi, yeah.
Zeta is something like this.
Yeah. Okay.
Yeah.
Psi plus 1 times n. Yeah. So by the way, this is we can discuss one thing that we will also use later in some form, that we have this one, and it's so this is not very good. For example, if I have a binary string, if my alphabet is binary, right? So my initial word is just of length n, it's n bits, and still we have here we have n bits. So I mean, ideally we would like to have this entropy times n plus, I don't know, maybe here I will have 1. So let me just briefly explain, well, how it can be done. So the point is that, okay, so we have our distribution, and let's consider, let's denote its probabilities by P1, Pk. So, and I want to code my word, well,
excuse me, just
I would prefer even like a, yeah. Sorry?
Before we start a technical explanation, can you say in one phrase, are you going to give a theoretical explanation, which is, roughly speaking, Huffman code for a huge alphabet, or you are going to construct a sort of arithmetic code, which is computationally efficient.
Yeah, well, I will not, I mean, I will just say that, yeah, well, basically
No, what
arithmetic
is
code.
important that this is actually this has nothing to do with Lempel-Ziv. It is just the code with which we can compare Lempel-Ziv code in terms of efficiency. So
Yeah.
here it's not important how effective is or what. It's just actually the lower bound is more important. So upper bound you can
No,
just
I
say
mean,
that you can achieve it by using blocks and
it's still useful to say how to get rid of this one here, because we will use the same trick later. So, I mean, let me just say it
okay.
quickly. So we can just use prefix-free codes again, but for letters, for sequences of length n itself, and for which distribution we just consider a distribution over sequences of length n, where we assume that each letter is sampled independently with, with these probabilities that we have in our distribution. And so our initial word, then, what is the probability of this word? It's like P1 times theta1, so on, Pk times theta k, and so it will be basically 2 minus theta I times log 1 over P1 plus theta k log 1 over Pk. So this will be 2 minus n times this entropy that we are dealing with, right? Because each theta 1 is P1 times n, and so on. And theta k is Pk times n. Okay, so what does it give us is that the another fact that exists, that it's not always true for the Huffman code, is that there are codes that, prefix-free codes, that if for words that have probability p, have length 1 over log p plus some constant. And yeah, so the idea is that now we can just to compress our string to something like that, instead of having 1 before the n, we should apply some code for the string, for the for sequences of length n, and then we will obtain, log of 1 over this. This will be just entropy of n times entropy of psi plus some constant, but now this constant is not multiplied by n. The other thing is
But
how
then
to do that.
the code becomes
Yeah,
dependent on n, which is not good. So I think it's all will confuse people, because if somebody knows this, it's already clear. But if not, it's not really necessary. Maybe you should switch to
yeah,
Lempel-Ziv.
but in my opinion, it's necessary, because I will use this fact, for example, that I just mentioned. Okay, so, and I mean,
sorry, wait, yeah, I can hear myself. If it is important, do we care about this constant, your big O of 1 notation? I think
no,
it is
we don't care
one.
about this constant.
Okay, so actually it's true with 1, well, but we don't care.
Yeah. Well, I mean, yeah, so like with respect to n, we won't care about this specific constant. And then I just wanted to tell that this already we won't use, that in fact you can do this coding in polynomial time by arithmetic coding. But I mean, in principle, such an encoding is possible, but it can also be done in polynomial time by arithmetic coding. But I mean, in the end, what I will tell you that this Lempel-Ziv, it will be much simpler and it will obtain, a better bound than, this complicated it's where you have to do this arithmetic coding for strings of length n. Okay. Okay, so next thing, then, okay, we use this, for example, Huffman coding, entropy for individual letters. There is this observation that, for example, you can have a word like that, 0, 1, 0, 1, 0, 1, and so on. And, okay, then, it has equally many zeros as ones. And if you try to compress this method by individual letters, well, you will have this entropy. So the distribution will be 1/2, 1/2. And so its entropy is 1, and you will not attain any compression. But now if you look just at blocks of length 2, then you already see that just the same block appearing every single time. And then what in general you can do, you can split your input string into, say, blocks of length 2 or in fact length 3 and so on, and consider these blocks as letters in a larger alphabet, and then just apply the same compression thing for these blocks. Here we will have just a distribution for blocks of length 2 that is considered that just one block. We always have one of the block, others are zeros, the entropy is 0, and and this will be just compressed as well as we expected, because it's a very simple string, just to 0. And yeah, so in general, so what we want to do next is that, okay, so as I was telling that I can split my input strings into blocks of some constant size, and I obtain in general some upper bound on Kolmogorov complexity of that string for every and possibly, well, it's not obvious, but increasing the length of the blocks, I will obtain better and better upper bounds of Kolmogorov complexity. So there are two things that I can explain. First, that actually, then you obtain some family of upper bounds of Kolmogorov complexity. And then basically you can define the same family. So it's a very rigid definition, robust definition. You can define it in some ways, and then, this family of upper bounds, this would be natural to call something like automatic complexities. So this will be one thing. So, mathematically, what will be the content is that possible content that I will give some definitions, and then I show that basically they are the same. And the second thing is that I can define Lempel-Ziv, and basically it will be the idea is that then there will be some very simple algorithm that beats and then it compresses every string, and then it gives some upper bound on its Kolmogorov complexity, and then basically in that sense, Lempel-Ziv will beat every automatic complexity function. So that's basically the content.
Yeah. So the idea is that first there is Lempel-Ziv. It's an algorithm which some fixed algorithm, and then we want to show that it's better than many other things, including the bounds obtained by this entropy of distributions on blocks. But the idea is that all these distributions on block coding, all of them are special cases of automatic coding in some definition. And then we don't care much about specific blocks, just we show that Lempel-Ziv beats all automatic decompressors, all finite state decompressor. say.
Yeah, repetition is a mother of education. So yeah, so then the next
I'm sorry, I have a question.
yeah,
Multiplicities of blocks should be included in the code, yeah?
multiplicities of the blocks.
Yes, in your example on the board, the length of the code should be something log n, because you need to specify the number of blocks.
No, but for a fixed...
It's not entropy plus constant.
No, for a fixed block length, we just have some fixed prefix coding, so it gets an overhead which is constant, but it doesn't depend on the number of block. It just depends on the length of block.
I don't understand. You insist that any word in the form 0, 1 repetition can be encoded in constant length? There are infinitely many words of this form. And finitely many words of any given finite length.
Yeah, so the fact that if you want, I'm saying that, this entropy gives an upper bound on Kolmogorov complexity, right? Yeah, I mean, formally, the upper bound, you should include some logarithmic stuff, for example, to include these frequencies of the letters, but it's just logarithmic information, right? We are interested more or less in the constant before n, in any case.
I see. So you will suppress any terms of magnitude log n and less.
Yeah, and like I will show for simplicity that Lempel-Ziv beats every this automatic complexity with just maybe with small of n precision, just not to care that I don't know exactly what.
I see.
Can it get
Thank
square
you.
root of n or something? So log n, it will be fine.
Okay, thank you.
So yeah, so basically, let me give other definitions. So okay, let's say definitions of automatic complexity. I mean, basically, you can, let me call them types. One type of automatic complexity. So basically, okay, formally, what it will be? It will be just each automatic complexity is just some function from the set of strings to, well, possibly to real numbers, not negative. That, the idea is that C of x will be just, this upper bound on Kolmogorov complexity. Maybe ignoring these log n terms. Now, so the first thing is that I already told, yeah. So you can take any fix k and define just the automatic, the complexity of x as this n. So what you can do, you can, so if you can split x, for example, into blocks of length k. Okay, there will be some constant overhead, but okay, we don't care. Then, so we consider these blocks of length k as individual letters in the alphabet, in the large alphabet. Then we obtain a distribution of these blocks. We consider its entropy, and then we just define the complexity is just this entropy of this psi times the number of letters in this large alphabet. Before it was just n, but now since these are blocks, then it's just n divided by k. Okay. And then, okay, so
yeah, and this is just
for every fixed k, we have some complexity, ck, and I will call these functions automatic complexities of the string. And then, as I described, again, this is like up to logarithms or something. These are upper bounds of Kolmogorov complexity. Okay, the second time I wanna. Okay, I will. The second time, for example, I want to define it in the style of Kolmogorov complexity, but the idea is that I will not use just all decompression algorithms, but only algorithms that are basically finite automata. So what is the finite state decompressor? I mean, the idea is simple. So we just have a finite automata. So there are like finitely many states. There is some fixed state, initial state. And then what this automata can do, it can read. So basically it will be a decompressor. So I don't know, it will obtain some word and it will map into our word X. So these finite state decompressors will perform, mappings from strings to strings. Well, from binary strings actually to maybe strings in some larger alphabet. And well, how it works? So it has states. There is initial state. In each step, it reads a letter of this input word. And then after reading this letter, it transits into some other state. And there are finitely many states. And also in each step, the automata can output a word which can be empty. So you can skip some steps, you can output nothing. But in some steps you can also output some word also. And this gives me some function from strings to strings. And then if I have some finite state decompressor A, I associate some automatic complexity function with it that is just defined as, well, as the minimal length of some string y that goes to X under A. Okay, so that's the second time. So are there any questions how this thing works?
No, I think you will have. It's a strange idea because you lose the superadditivity and you will have troubles. And okay, but if you want, let's do this.
Yeah. Well, I mean, superadditivity.
But it is more general, right? Because any compressor that is in terms of letters can be turned into finite state.
Sorry, you mean it is more general than what? That the decompressor, I don't know, like a transducer that receives a letter and outputs a letter or something like that.
Receives a letter and outputs a sequence of bits, right? The standard formulation. And for every letter, we output a sequence of bits.
Yeah, but I defined it as, like that. So there is a function from states to words over sigma. And then, so basically in any state, in any moment, you're outputting some possibly empty sequence of letters of the alphabet. So you can read a letter and output something. I mean, 3 letters, depending on your current state. You read a letter, then depending on your state, maybe you don't output anything. You read next letter, maybe you output something or not. Again, and this just depends on what is your current state. You have your state, you receive the letter, you output
Yeah, and I understand
something
that.
depending on your state.
So my question is it known that this class of the compressor is more general, strictly more general than more powerful, than just the standard definition, where for every letter I have a fixed sequence of bits.
When you say that, you mean just you?
Yeah, if I
you
have
just consider.
say Hamming encoding or some like other way of encoding, such that every letter is encoded in a fixed sequence of string, I understand how to construct an automata that do the same, right? But the
But I
other way
mean,
around is not clear.
So you mean, like, for example, if you have 0, 1, 0, 1, 0, 1, 0, 1, then you're suggesting just to replace all zeros by some one word and all ones by the other word, regardless of.
Right.
As I see, any prefix code can be decoded by finite-state decoder, deterministic one.
Right.
Is it the
Yeah.
answer to your question?
So no,
Yeah, basically, I
this
think
direction I
Sasha was
understand.
answering.
But my question whether the class defined by automatas is strictly larger or strictly more powerful in terms
It
of
seems
encoding.
that it's a strictly larger, right? But because you're suggesting to just have some alphabet coding for individual letters, right, of the word.
Right, or like where we can.
And then if you have a word like 0, 1, 0, 1, 0, 1, 0, 1, I mean, it won't give you any compression, but you can basically compress it by automata as much as you want. Because, for example, give me one, I have to. Okay, I think it worked. For example, we can describe. So for example, well, so the question. So let's say we have a word like that. How to construct an automata that compresses it? I don't know, 10 times or 100 times. In that definition, in the finite-state decompressor.
Okay,
definition.
so now I see. So you can just add some additional like small automaton, then just count.
Yeah, so basically in that
count the
definition
number.
you can just have an automata that outputs 100 pairs 0, 1, 0, 1, 0, 1, whatever
Right.
it
Right.
receives.
For any
And then this word has a code of length actually like 200 times smaller, and you can make it arbitrarily small to 0. Okay. And then the third type that I want to consider, maybe I'll mention some other types, but okay. The third time is to define it somehow axiomatically, this automatic complexity. So let me define. So let me say that a function from words to non-negative reals is automatic if it satisfies two properties. One is that it's superadditive, means that if I have a concatenation of two words, then the complexity of the concatenation is at least the complexity of x plus complexity of y. And the second property is that there exist not so many strings with complexity at most n. Most precisely, there exists some constant c. Yeah, it's the same letter, but okay. There exists some constant a. Again, I mentioned it. B. Okay. There exists b such that for every n, the number of x's such that c of x is at most n is at most c times 2 to the n. Oh, sorry, b. That this constant that I was carrying off. Okay, so basically it has to be superadditive, and then it has to be like it has to mimic, Kolmogorov complexity in the sense that in the Kolmogorov complexity the number of strings of that complexity is at most n is at most 2 to the n. But here we won't have this nice superadditivity property. We should allow us to have maybe some larger constant, but still a constant. Okay, so basically I defined three families of, you can define more, but let's say we have three families. So we have three families of automatic complexities. And I just want to show that basically this is not literally the same families of functions, because, for example, this superadditivity, the other two won't have exactly these properties. So what I want to show some robustness of this definition is that
I'm sorry,
okay,
to be clear. So repetitions does not help. If you have a string xxx, its complexity is 3 times complexity of x, at least.
Yeah.
Yeah.
Well, it's strange to me because Lempel-Ziv uses multiplicities to compress the code. But, well, okay.
But that's exactly not the part of the Lempel-Ziv.
No, first it's another Lempel-Ziv which use I guess which use multiplicity. But let's wait until Lempel-Ziv will be introduced before discussing this.
Yeah. Yeah.
But why any automatic complexity satisfies superadditivity?
Why?
Up to a constant. No, that's true, but maybe Sasha will explain it. Just.
Yeah, well, they won't satisfy superadditivity, but basically the idea is that you can change a function just a little bit so that you can satisfy the superadditivity. So basically what I want to show is that, I don't know, for example, the statement that for every automatic complexity, so let's say I have automatic complexity C1 of the first type. And then I'm answering, well, what about type 2? Can I have an automatic complexity which is at least as good as this C1 but of type 2? The answer is yes, but okay, with some margin, possible margin, that for every, so if I have an automatic complexity of type 1, and then for every epsilon there exists an automatic complexity of type 2, C2, such that what I want to write is that for all n and for all words of length n, well, maybe for all sufficiently large n, let's say, let it be more precise, for all sufficiently large n and for all words of length n, C2 is at least as good up to constant epsilon in the length of the word. Well, it's n. Yeah. And then, I mean, this is just the same holds for any pair of types.
So in the first, when you say for every automatic complexity C1 of type 1, it actually means for every k.
Yeah, for every k.
Yeah.
I mean, but I'm stating that there is a similar statement for any pair. Pair of types, which means that somehow in the limit, all these functions, well, okay, it's a if we like define the same upper bound on Kolmogorov complexity, if one family of functions gives some upper bound on Kolmogorov complexity, then the other there is a function on the other. Yeah.
What is about the previous example with 0, 1 repetitions? You have explained that automatic complexity is much less than complexity of type 1.
But automatic complexity will be smaller than epsilon n. C1 of x is 0, but epsilon n covers automatic complexity if we choose a large enough size of block. We just encode large block by 1 bit, and then we repeat these bits and get epsilon n for
I see.
we want.
Yeah. So I guess I would like to prove this thing. Let's try to first prove it. And okay, so we have three types. So what do we have? We have entropy. We have automata. Entropy is the first type, automata is the second type. Then we have superadditive functions the third type. And then the proof, I guess the most simple thing is that you show that if you have an upper bound, so there is some upper bound on entropy, then you can construct an automata that witnesses this bound. Then if you have automata, you can construct a superadditive function. And then basically in the end, you also, you close it by showing that if I have a superadditive function, then and I take large enough blocks, I obtain this entropy, and this gives me the lower bound of these superadditive functions. Okay. So let's try to show it. Okay, let's discuss this direction. So what it gives, I have a automatic complexity of the first type. So basically what I have is that I split my word into blocks of some length k. And maybe there is some rest, but I don't care. And then I took a distribution of the frequencies of the blocks, and I have this quantity. And my goal is to construct an automata that gives me an automatic complexity, this quantity, and I'm allowed to have some epsilon n here, right? But somebody gives me small epsilon, positive epsilon, and then I have to give some automata that gives an automatic complexity at most this.
I'm sorry, in automatic complexity, do you include the size of automaton?
No, I do not include it because, I mean, yeah, for a fixed automata, this is just a finite piece of
Not any string
information.
has constant complexity, because for any string I can write an automaton
No,
of
this is
very
not.
large
There is
size.
not a thing. No, you don't fix a string and choose an automaton. You fix automaton, and then you have function on strings.
Yeah. And then you compare these
this
functions.
function cannot be constant. But of course, for any string, we can find a function, an automata who makes complexity of this string 0.
Yeah, I mean,
It's a bit
likewise,
like
you can.
Kolmogorov complexity.
As I understand, the automaton depends only on k and epsilon.
I see.
The automata will depend only on k and on epsilon. I think that's true. Well, basically, it has to, because I have to give some function, some automatic complexity of the second time that just depends on k and epsilon. Yeah, that's true. Okay, so, well, what's the basic idea? The basic idea that we can achieve this compression by automata, because what we can do,
We just use
we can
coding, Huffman coding for k-bit blocks, for k letter blocks.
Yeah, and it can be done by automata, right? Because, so we consider this Huffman coding for this distribution, and then our automata, well, how it works. Basically, the code
But this
will be,
distribution depends on a word. I don't
Sasha,
understand.
wait a bit. Are you proving the first inequality from 1 to 3? Or
No,
from 3 to 2?
between 2 and 1. 2 doesn't exceed 1.
The last one.
Yeah.
You are proving the last one from automata to entropy.
Yeah.
Yeah, but actually you need to use universal, you need to cover the space of all distributions by small neighborhoods.
Sasha, then one have you started with dividing your string into blocks?
Because entropy is defined as block frequencies for some k. So we just take this k.
So we are given an automaton, and we want to find...
No. We are given an entropy complexity, which means that actually we are given k.
Sasha, which inequality we are proving now?
The last one.
The last
automaton.
We are showing this statement that if I have an automatic complexity which is obtained from entropy of blocks, I can have an automatic complexity defined in terms of automata that is at most
sorry,
at least as good as this.
I
so
just
we are proving the first inequality.
I'm sorry. Right.
Yeah, so regarding the how to actually have an automata, yeah, well, the problem, there is no problem actually with the fact that automata cannot read, doesn't know the Huffman coding. Because you can, so the Huffman coding we have is for blocks of length 2 to the k, right? And then we basically can have an automata that reads these in the beginning. We have in the description the description of this Huffman coding, and also if I have a Huffman coding for for the alphabet of length 2 to the k, then the length of any coding word is bounded, because I mean it's bounded by the length of the by the number of symbols in the alphabet, right? Because the way it works. So basically, in the end, you have just, basically finitely many different Huffman codings for 2 to the k, for blocks of length k.
No, it's not so clear, because when you increase the block length, then you increase the probabilities. No, sorry. No, maybe it's not. So if k is
No,
fixed,
because the Huffman coding, it's like, how it works, if you remember it,
oh yeah, you say you can just write the code in the beginning.
yeah.
And the size of this prefix depends only on k, actually.
The size, and this is this is kind of important, that it's a constant, so we can have an automata that is
Constant with
programmed to
respect to
use.
the length of word. Yeah.
But
Yeah,
then
constant with respect to.
but the inequality will be then true only for large n.
Yes, and the theorem was stated in this form.
Only that, yeah.
Yeah. But actually, still, we will have this one in the
So when we use
so
Huffman code, we get some overhead. And to get rid of this overhead, we need to switch to longer blocks, actually. That's what is the problem here. So we get...
yeah.
But now we
Well,
simulate
then,
the blocks of fixed length k. The theorem is, if you take k and epsilon, you can construct an automatic complexity.
But first, given k and epsilon, you construct some bigger k, which is some constant times k, and the constant depend on epsilon. And then for long n, you use these bigger blocks. That's what is the plan.
Yeah.
So if you multiply the length of blocks by 2, then you just get 1/2 of instead of 1.
yeah, but
it's not
then,
completely
Sasha,
obvious,
you
but
will.
Yeah.
This is not obvious, and I had another way to explain it actually.
Okay.
Because then you're saying that, okay, we can consider blocks. So now in this form, if I just have this, right? So I have this n over k overhead, and indeed, if k is large, then this is just a small overhead. But my epsilon can be, smaller than 1 over k. And then indeed you say that I want to go to a larger block size, and I want to say that, this entropy upper bound can only become smaller, and then I can use and construct automata for larger blocks, and then this overhead will be smaller. But then, um, then then
You need
then we have to
convexity of
explain
entropy,
somehow.
but it's not something difficult.
Yeah, I mean, I had another way of explaining things,
Okay.
I think, that doesn't use any information. Well, I mean, then that avoids this stuff. Basically, the idea is that I want to indeed now, so I have these blocks of length k, and I have my distribution p1, pk. Now I want to split these blocks, but I don't know. I want to I want to merge, these blocks into groups of some fixed size. So let's say I want to take each three blocks, and then I want an automata that will work by producing, these three blocks, then these three blocks, then these three blocks, and so on. By in general, like morally, what I did is just I increased the block size. All right, and then what I want to do is to encode every such block using, for the distribution, so now I have, like, for example, so I have a prefix recoding over blocks of over words of length 3k, right? And now I want to consider just this Bernoulli distribution. So basically, so we have a triple of blocks, and then its distribution is, I don't know, if this is the second block, this is the first block, this is the fifth block, then the probability of this block is p1, p2 times p1 times p5, and so on. So my idea now is to use, for every triple of blocks, this, for example, this arithmetic coding or whatever, any prefix-free code that uses at most log 1 over the probability of this thing, and then there will be this constant overhead.
Okay, let me say what you are doing. So, of course, if we can take just a bigger block of size 3k and consider their actual distribution. But then we need to prove a bound for entropy of their actual distribution. But instead of that, what Sasha is doing, we use for blocks of triple length, we use the code which is optimal for other distribution, which is just the independent sample, three independent samples for our distribution. And in this way, we get code of correct length without using, somehow we prove in this way, we somehow reprove the convexity of entropy.
Yeah. And then I'm just saying that, like, the idea will be that all these terms will sum up to, as we see, to the entropy times m times k. But now this constant is divided not by the number of blocks, but not by the length of the block k, but by 3k, right? And then by taking larger and larger blocks, you can make this thing go to 0 and make it smaller than epsilon. Now there is
But
again.
now you have
this...
another problem. You should realize by automaton this arithmetic coding.
Yeah, so that's another problem. For that, I wanna now, for example, I wanna describe in the beginning of my code. I wanna
we use just Huffman code for auto distribution and the bound entropy +1, which we believe in.
No, Sasha, we don't use Huffman code because Huffman code doesn't have this property that the length of the word is log divided by 1 of the probability in general, plus something. We have to use, I don't know, any prefix-free code with this property. But then,
okay, so we use actually what was used in the proof of Huffman code.
Yeah. The problem is again that we have to also describe this prefix-free code that we are using in the beginning of the word, and it has to be constant independent of n. Okay, so we have a prefix-free code for words of length 3k for sigma to the 3k. But now this is actually okay. These probabilities are whatever, and so the idea is that, as Sasha was saying, that so basically I'll have some probability distribution of these words, and then the code length of a word will be 1 divided by log p of x thing. Yeah, so this will be bad if because then I cannot bound in general this by any constant, right? If it's small, then because I mean I have to have some finite number of states in my automata that reads a prefix-free code, but then this prefix-free code has to be have some bounded length. So the way we can solve it is that let's just do the same compression, but with some distribution Q, and Q will be just, one of finitely many distributions. So basically, we can achieve after small margin that depends on epsilon, we can achieve the same bound by just, so we have a, some compact, so we have a space, we have a set of all distribution over 3k strings of length 3k, and this is a compact set, and entropy is continuous there, and hence it uniformly continuous, and it means that basically you can choose finitely, if you give me some delta, you can choose finitely many distribution such that for any distribution there exists one out of this finitely many whose entropy differs by at most delta. And then the automata, and then, okay, then all these distributions have some upper bound on this Q. And then basically it says that if you are interested in this, just in beating this epsilon, you can always fix the length of the prefix-free coding that you are using. I don't know, is it any clearer or?
No, I think that what I understood in advance, I still understand, but it's I'm afraid that the explanations do not help much. But just let what others say.
I think it's clear. We can proceed to another inequality.
Yeah, so in the another direction, I
So
want to
to be
come
sure about the first inequality, so in this way we obtain an exponential blow up in sizes of automata with respect to k and epsilon.
Yeah, I think it's exponential, right? Because
They
it has to
don't
be.
depend on n, but if we compare the sizes of automata and the length of k and epsilon, the blow up is exponential.
Mhm. Well, I
Okay.
mean, it has to be more or less because you are reading the word and the block itself, and then you have to to the case states to remember what.
Yeah, okay, I see, but just to be sure that I understand.
Yeah. Okay. So in the
No,
so
what
then
Misha says, maybe it's actually an interesting question. If you want just to finally get a connection between entropy bound and Lempel-Ziv bound, then there is some kind, there will be some function on k, and it would be interesting to see how large is this function, but it's another story.
yeah, I think it's like yeah.
It's
Yeah,
a
yeah,
Let's
story
okay.
say
about practical algorithms, because if you use automatic complexity decompressor or entropy decompressor, it is a question how they are good enough in practice with respect to Lempel-Ziv. It is the main motivation, as I understand, of all this talk.
yeah. Okay, so next I wanted to explain how to get from automata to superadditive complexity function. So Sasha will was predicting that I will have some problems here, but I think that that's not true.
No,
But
no,
let's see.
you need to switch to different type of automata first. So
Yeah.
yeah.
So basically, so I have an automata, right? So some automata A, and what happens is that it reads a symbol and maybe outputs. So it reads and then outputs a word. And then this repeats until we see the length of the word. So it will, so to go from automata to superadditive function, we have to um, modify it into another type of automata that basically like a, how to say it, like discretized type. So basically, let's consider an automata that depending on what is this its state, it can either read a letter or maybe an output a letter, but not at once. Well, so basically in this kind there will be just two types of states. In one types of states you read the letter. In the other types of states you just output a single letter, and then basically you just go through some cycle again because there are no letters. And here you have a some state and you receive a new letter and then you update your state, right? So there, and the point is that if I have some automata that I define initially, I can transform it into this type of automata, right? Because if I have that achieve the same compression, right? Because basically, I mean, if I have a state and in this state I'm outputting some word of some length, I can introduce, you know, key more states that just go in a cycle and output these letters
So
in t
without
steps
reading anything.
without reading anything.
Yeah.
So now I assume that my automata A is of this discretized or quantized type, and then and this was achieved by maybe increasing the number of states. But what I want to define next is to define a complexity function associated with it, which basically the same thing as the complexity in terms of A, but what I also allow to do that before, you know, how was C of AX defined? Is the minimal length of Y that goes to X under Y. But here we assume that A has some initial state and it starts in the initial state. Let's also define a complexity that that is just which we also allow to minimize over the states. So this is a minimum over Q, and then again this is the minimum of Y such that A from the state Q gives me X. So one thing is clear is that this thing is just possibly smaller than my initial complexity function, right? Because I took another minimum, I allowed to change the initial state. Then we have to understand that this is superadditive, and then that this has properties that like a Kolmogorov complexity, that the number of strings of this thing is at most to the n times some constant. And then that this is superadditive. So we have to understand these two things. Well, this is more or less clear, right? Because if we didn't have this minimum,
it's not enough because you will prove only that the new complexity is superadditive, but not the old one.
I'm not trying to show that the old one is superadditive. I'm trying to show that if I have a complexity of some type, in this case, the second time defined by automata, I can transform it into complexity of the third time that should be superadditive, that has achieved the same, which is at least as good as my initial complexity. But there are no statement that this initial complexity is superadditive.
Okay, so then you will need to prove that it is close to the initial one. Okay.
It's
well,
bounded.
I don't have to prove.
It's an upper bound. It's
an upper bound on the initial one.
Complexity,
I mean,
automatic complexity
C of
is
X,
bounded by some superadditive function, which is.
So I only care about this inequality.
I see. I see.
Well, I mean, in principle, you can imagine, yes. So in this, I can obtain something better if I start from, if my actual automata is from some unreasonable state, and then if I take the minimum overall states and it becomes much smaller. But then, okay.
Okay, I see.
Yeah, so this thing holds just because, I mean, if we don't have the minimum over Q, then we have a single decompression algorithm, and then the number of strings that have complexity at most n with respect to this decompression algorithm is at most 2 to the n. Right? And then I'm just taking the minimum over finitely many decompression algorithms, and their number is basically this B. And this Q is actually, let me just say again that it's larger than the initial automata that can output a string. It's the number of states into this new type of automata that either reads a letter or outputs a letter. And then, so we took this minimum of states to prove that this thing is superadditive. Because, okay, so we have, so basically, so let's say I have a concatenation of two words, X and Y. And, well, actually I had Y here, but okay. And then there is some word Z such that under some AQ, for some Q, it goes to, it produces me the concatenation of X and Y, which proves that and I take this Z that achieves this, such as the length of this Z is achieve this minimum, right? So the complexity of X and Y is the length of this Z. So this is the optimal code with respect to this thing. Now the only thing, the only idea is that, okay, now when when my automata works on Z from Q, I can consider the first moment when it outputted X, and this happened after some Z1. And then after that, it came into some state. So it started from Q, then it came to some state Q1, I don't know. And then there is the rest of the Z, which is Z2, and it gives me Y. Z1 gives me X from Q. Z2 gives me Y from Q1, from possibly another state. But still, whatever state it is an upper bound on complexity of K. And then the other thing is the upper bound of the complexity of Y. And we have this inequality. C of xy equals Z, and these things are smaller than, it was length of Z1 and Z2, and the sum of Z1 plus Z2 is the length of Z. Yeah. Okay. And the last, what is left, is to show that if I have entropy, the inequality that entropy bounds superadditive functions. So basically, if I have a superadditive function, C is a superadditive automatic complexity function, then for every epsilon, there exists K such that if I consider the entropy obtained by blocks of length K, this will be at most my initial superadditive complexity function plus epsilon of the length of the word for all large enough n length of the words. And this is this direction is just easy of the by the definition of the superadditivity, right? So we have to obtain a lower bound on C of x, right? So basically then we can lower bound it by, we can split it into blocks of length K and upper bound it by the sum of complexities of these blocks, right? Okay, so then what we will have? We will have the sum overall words of length K that are potential blocks. I don't know, let's say, how we know to type beta, let's say. the value of my superadditive function on beta times the number of occurrences of beta, right? And this is if we normalize by the number of blocks, this is the sum of my where instead of the number of occurrences, I have I have this probability distribution which is induced by this number of occurrences. Yeah, and then basically I have to show that this is at least, you know, the same thing where I have the entropy of this distribution and I allow myself some small epsilon n. And this is basically the standard thing, you know, this this concavity of log. So how does it treat it? So you can show it like
I think you can just say that the automatic complexity, this superadditive function, you can take an upper bound, which is standard Kolmogorov complexity, and then you replace the standard Kolmogorov complexity by prefix complexity. For prefix complexity, you just have a real prefix-free code, and you can apply bound for prefix-free codes. No?
No, I'm not sure because we have constant length in any case. And then all these upper bounds on Kolmogorov complexity, I mean...
No. You choose length for entropy. So you can take arbitrarily long block size. What is the problem?
Yeah, but okay, then how do you argue that this superadditive
superadditive function is upper bounded by Kolmogorov complexity.
And why is that? We haven't shown that yet.
Because we know that there are, for any element, there is at most constant number of...
But I didn't say that it's computable in any sense.
Okay. You can say use Oracle if you want. If you want to be formal, you can use Oracle. It doesn't matter. Okay, but no. If it's not. No. I'm afraid trying that my explanations will make things even worse. So just feel free to ignore them.
I think that we could just make a standard this derivation, so we can just look at this difference. For example, the difference of the entropy minus the same thing, but the sum of these things with blocks. And we have to show that this is at most epsilon n. And this difference is just, okay, let's have the number of blocks here. The entropy is the same sum of the strings of length k with these probabilities. And I have one beta. And then here to put, so I have minus, so I will have here. So this difference I just rewrote like that, right? The difference between entropy and the sum of the values of my superadditive functions on betas. I put 2 to the minus c beta into log. Then, well, this is the most then log of the average, right? But then these things cancel out, and I just have the sum over blocks of length k of 2 to the minus c beta. And then it's just finally I used the fact that the number of beta goes with the value of c beta, which is some n, is at most 2 to the n, which basically says me that, okay, I can have how many strings of complexity t I can have at most 2 to the t, and then they are counted with this coefficient. So basically, I will have the sum from 1 to k of 1, so this will be log k.
And why it is up to k? I don't see why the complexity can't be very large. Complexity of a block.
Large is good for us because we have summation over 2 to the power minus complexity. And small complexities, they are not many.
Yeah, okay. So how to?
Maybe we can say if the complexity is larger than 2k, then we can upper bound it by another argument, just knowing that the total.
Yeah. Then if the complexity is larger than 2 to k, then the number of such strings is most 2 to the k, and then it's just.
Okay, I see.
Mm-hmm. Yeah. And then the point is that, yeah, it's n log k times k, and this becomes as small as you want. Yeah, okay, so that's it, I think, for today, because...
Yeah, but no, just...
failed miserably.
No, okay, but it's a good preparation, because I guess the next time we can provide a clean explanation of what is this Lempel-Ziv code and why it's good. You may be using something which was explained today, but I guess that it's not assumed that today's facts are really understood, because I think it was very difficult to follow, and so I guess the next time will be Lempel-Ziv again, but somehow more or less independent from what was today, so we can even if you didn't understand anything, it should not prevent you for getting maybe not all but almost all information next time.
Next time it will be Lempel-Ziv itself.
Yeah. So next time I think we'll start with Lempel-Ziv, and then try to... Actually, I can tell you the secret. The most important thing is Lempel-Ziv is that all the strings are different. This is the only thing which is really needed, and together with superadditivity, it immediately gives, and very easy bound, it immediately gives whatever is needed. But so everything will be very simple. Don't be afraid of by this preparation today is not much more difficult than the entire thing, I guess. No, it's also it's a good approach, but it's not all needed.
But, are you saying that those people who are lost today shouldn't come next week?
No, they especially should come because it will be a rehabilitation process. They will healed by providing a very simple and clean explanation of Lempel-Ziv.
Okay, let us hope for better.
Yeah. It's so today somehow the main point which is that we can estimate to compare to prove that Lempel-Ziv is efficient. We prove that it's better than any superadditive bounded function.
Yeah.
And then this is completely simple and obvious, almost obvious. And then there is all the rest is the explanation why this entropy superadditive functions cover all the Huffman encoding things, and the reason is because this Huffman encoding things are automatic, and automatic are essentially implies immediately the superadditivity up to some constant. Okay, but just we will try to I think last time it will be next time it will be much more easy to understand. So if you didn't understand, don't worry. That's what I want to say. Yeah. Okay. So if anyone wants to give another talk at our next one
time.
of the next, not the next time, no, we can make a break, but if there's, we can also make some planning for talks after that. So please contact. Yeah, for example, Lyosha Milovanov should explain us what Hirahara is doing at some point, I guess. But maybe he doesn't know it yet. Okay. Okay, then we will continue, or better to say, start anew next time.
Yeah.
Yeah. Good. Thanks.
Thanks.
Thank you.
Thank you.